going to go through two solutions to these problems, starting with a polynomial problem. We have a polynomial here, and notice that there are two unknowns in it, p and q, and we're given two pieces of information. The first one tells us when f of x is divided by x minus 1, the remainder is minus 28. And that is basically telling us that f of 1 is equal to minus 28. The second thing, when f of x is divided by x minus 2, the remainder is 0. And it's telling us that f of 2 is 0. So, these two facts are going to let us create two equations in p and q, which we're then going to solve simultaneously to work out what they are. So let's start with f of 1. So f of 1, as we know, is equal to minus 28, which is equal to 2 times 1 cubed plus 7 times 1 squared plus 1 times p plus q. And that simplifies down to 2 plus 7 plus p plus q, and of course it equals minus 28, and that in turn simplifies to p plus q is equal to minus 37, and that is our first equation. Now we're going to do f of 2, and we know that that equals 0, and we've got 2 times 2 to the power 3 plus 7 times 2 to the power 2 plus 2 times p plus q, and that gives us 16 here plus 28 plus 2p plus q, and equals 0, and then we subtract that over and we will end up with 2p plus q equals minus 44. And I can't emphasize enough how careful you have to be to get these right. Take your time and be careful. So now we've got our two equations, we can solve them simultaneously. So I'm going to write them one above each other. In fact, I'm going to take this equation here and I'm going to double it. So I've got that one. So I've got 2p plus 2q equals minus 74. And on the bottom I've got 2p plus q equals minus 44. And to eliminate the p's, I'm going to subtract, which means I've got q equals minus 30. Substituting into 1 gives q as minus 7. So there's my intermediate stage. Now I can go back to my polynomial and substitute these in, which means that I've now discovered that f of x is equal to 2x cubed plus 7x squared minus 7x minus 30. And if you'll notice, I've just put p in for as minus 7, and I've just spotted that should be a p there, shouldn't it? Hope you spotted that. And q is minus 30, and just make sure you get them the right way round. Now, I've done this, and now I'm going to fully factorise f of x. And to do that, I'm going to use the fact that they've actually told me one of the factors. This is a factor, because when you divide something by a factor, you get a remainder of 0. So I know that if I divide it by x minus 2, then what I have is the other factors. So I've got x minus 2, and I'm going to divide 2x cubed plus 7x squared minus 7x minus 30. Okay, so first of all we take the x and we say how many x is going to 2x cubed, and the answer is 2x squared. Then we take this and we're going to multiply it by each of these things here. So it's going to turn 2x squared times x gives us 2x cubed. 2x squared times minus 2 gives us minus 4x squared. And we subtract. So that's going to vanish, and this is going to leave us with 11x squared, because 7x minus minus, see the double minus, 4x gives 11. This drops down at this point, and we do it again. x is into 11x squared, go positive 11x. Then we take our positive 11x and we multiply it by each of these. So 11x times x is 11x squared, and 11x times minus 2 is minus 22x. These disappear, that's the point. Minus 7 minus minus 22 gives us positive 15x, and then the minus 30 comes down at this point, and we do it again. X is into 15x, go positive 15. Positive 15 times x is 15x. Positive 15 times minus 2 gives us minus 30, and then when we subtract we get 0, which is a great relief because that's obviously means that we've done it right. So we can write f of x as x minus 2 times 2x squared plus 11x plus 15, and I got that from here. And then to finish off, I just need to factorise that quadratic, and it factorises nicely into 2x plus 5 and x plus 3. And if I was sitting an exam, then I would jolly well multiply that out if I had time at the end just to check I'd done it right. Question 2. Pardon me. Okay, a bit more tricky. So, we've got a cylindrical can. So, where possible, a diagram's always a good idea. It's got a radius of r, and it's got a height, rather unimaginatively, of h. We're asked to find an expression for h in terms of r, and it's obviously got something to do with the capacity, and what they're telling us there is the volume, the capacity. So the volume is 2 litres, which is 2,000 millilitres, which in turn is 2,000 cubic centimetres. So that's the volume. The volume can also be represented by r and h. So the volume is pi r squared h, and that is 2,000. And I'm now going to rearrange it for h. So h equals 2,000 divided by r squared, pi r squared in fact. So that's the first part. Now, hence, find an expression for the surface area of the can. So that hence is telling me that this is going to become useful at some stage, and it's got something to do with this in terms of r only. So I'm going to have to use this to get rid of the h. So let's go for it. Surface area, call it area, is equal to, so I've got two ends, the top and the bottom, so that's 2 lots of pi r squared. And then I'm going to have the big rectangle that's wrapped around the middle. Now, that rectangle is going to be h high, and then this length here is going to be the circumference of the circle, so that's 2 pi r. So it is 2 pi r each. But we want it in r only, and this is where this last bit comes in. So area equals 2 pi r squared plus 2 pi r times 2,000 over pi r squared, and that came from here. Notice I've turned the h into this bit. A bit of cancelling can go on here, that can cancel with that. That r is going to cancel with one of those. So that gives us area equals 2 pi r squared plus 4,000 over r. Or, and this will become apparent in a minute why this is useful, plus 4,000 r to the minus 1. Now, finally, find the value of r which minimises. So minimises, you need to think minima. And of course, this is a curve and it's going to have a minimum on it. So we will just have to find the minimum. We start by differentiating it. So dA by dr is going to be 4 pi, oh I lost my r didn't I, pi r, minus, because the minus comes down, 4,000 r to the minus 2. Now, turning points, the gradient equals 0. So 4 pi r minus 4,000 r to the minus 2 equals 0. Rearrange it, 4 pi r is equal to 4,000 over r squared. Multiply the r squared up. 4 pi r cubed is 4,000. R cubed, 4,000 divided by 4 pi, which equals 1,000 over pi. So r is equal to the cube root of 1,000 over pi, which turns out to be 6.8 or thereabouts, and it's this is centimetres, because we started with centimetres here. That's where our centimetres come from effectively. Now, let's just check it's a minima. So we're going to differentiate it again. d2a by dr squared is equal to 4 pi plus 8,000 r to the minus 3. And if we put a positive value of r into this, then we get, and we're only really interested in the sign, if we put a positive value in, we're going to get a positive value out, which means it's greater than 0, and that means it's a minima. Why is that? Well, if you consider a curve doing this, then the gradient is going from negative, so it's going downhill there, to 0, there's a little bit at the bottom where it's flat, to positive. So the gradient is actually increasing, it's going from negative to positive, and that happens at a minima. So the gradient is increasing, it's bigger than 0, this is. If it was a maxima, then it would be a positive gradient going to 0, going negative, and of course positive to negative is decreasing, which means this would be less than 0. So there we go, that is the end of the question.